All right, good afternoon, everybody, and welcome back to 6854 Advanced Algorithms. We're going to be continuing to talk about Fibonacci heaps today, and then I'll introduce you to persistent data structures. Some administrative stuff first. If anybody's having trouble hearing me or there's other problems, now would be a good time for me to know. In terms of collaboration groups and office hours, actually, I'll save that for later because people will probably be coming in late. So I'll make some of those announcements later on. We've determined that the echo that you may be hearing is caused by my microphone rather than by my room. So I'm going to have to acquire a new one. And, sorry for the echo in the meantime. So let's remember where we left off with Fibonacci. We had designed this approach based on heap ordered trees. And a data structure that was a collection of them where we used union by rank to keep the degree small. Right, we arranged that if you had a degree D tree, then you would have 2 to the D nodes in that tree because the sorry, one second. Because that tree essentially represented D rounds of a tournament to select the winner among all of the nodes in the tree. And we had some mechanisms for insert, where you just create a new heap ordered tree. And delete min was where things got interesting. We would remove that minimum and then perform a consolidation to reduce the number of heap ordered trees and find the new min. And the key insight was that if you're going to have to do all of this work anyway in order to find the next minimum, let's use that work in order to simplify the data structure so that we don't have to do as much work the next time around. Oh, that's not what I wanted to do. There we go. Starting so nervous with all of this remote technology. Okay. And the way we analyzed this was using a potential function. The potential function can be whatever you want, but then you define the amortized cost of operation I to be the real cost of that operation I plus the ending potential minus the starting potential. And that means that the sum of the amortized costs is equal to the sum of the real costs plus the final cost minus the starting cost, right? And that means that it is greater than the sum of the real costs if the final potential is larger than the initial potential. For example, if the initial potential is 0 and the final potential is greater than or equal to 0. Right? So we define this notion of a potential function and used it to define an amortized cost. And if we use the right kind of potential function, then the total amortized cost of a series of operations upper bounds the total real cost of that series of operations. And so we can declare that the total work that we did is upper bounded by that amortized cost. So for Fibonacci heaps, we define the potential to be the number of heap ordered trees in our data structure. And we noted that on an insert, well, the real cost of that insert is 1. We're doing a constant amount of work to create the new tree. And the change in the potential is +1 because we've added a tree. And that means that the amortized cost is equal to 2. It's constant, right? As for the delete min, well, if we start with T trees, we know that we are going to end with at most log n trees. Remember, somebody remember why that is?
There's only 1 tree per rank, and
exactly. We consolidate by ranks, and we end up with at most 1 tree per rank. So we end up with only log n trees. And that means that the change in potential is at most log n minus the number of trees that we eliminate. Right? The real cost is equal to, well, we have to consolidate the trees, and that takes us T time. And we also create log n new trees. Where do those come from?
When you remove the minimum,
Right.
the subtrees will be split up.
Exactly. So this is the children of the minimum. So if we add these up, the amortized cost is equal to 2 log n, or order log n. And so we already had in our Fibonacci heap a data structure with a constant insert time amortized and an order log n delete min time. Okay. So where we got stuck at the end of last lecture was decreased key. The obvious thing to do with a decreased key is to maintain the heap invariance, right? So we would cut the key from its parent to get our heap invariant back. Right. The problem with decreased key is when you end up with a violation of the heap invariant because the child has become smaller than the parent. And of course, it's a heap ordered. It's the root of a heap ordered tree, so we can add it to the heap ordered tree list. Right. And so far, that seems fine. We've introduced 1 more heap ordered tree, which adds 1 to the potential. That's only a constant. We've done a constant amount of work. Everything looks good. What problem did we encounter?
We lose the log n trees bound.
Right, we lose the log n tree bound. And why do we lose the log n tree bound? Sorry, which log n tree bound are you referring to? That we have log n heap ordered trees at the root? Sorry, at the after consolidation?
Yeah.
That actually, I mean, we can continue to have that because, or at least it would seem that way, because that log n comes from the fact that we just have log n buckets, right? 1 for each tree size, 1 for each power of 2 in tree sizes. And we're still going to have, you know, at most size n in any tree, so it would appear that we only need those log n buckets.
The size of a rank I tree can be like small.
Right. The problem is that this can decrease the size of a rank R tree. Right. We've just removed some nodes from the tree without changing the degree of the root. It's the degree of the root that determines the rank. So all of a sudden, trees of rank D no longer need to have 2 to the D nodes. And if that's true, then it's possible that we may end up with a lot more, right? If you can't use that bound on the number of nodes in a tree, you may end up with a tree that has much larger degree than the log n that we originally proved. So that's what we have to fix. And this is sort of the moment in the design of the data structure where the real creativity hits. I think everything we've done so far, basically makes sense for the design of this data structure. But here, Fredman and Tarjan thought of something pretty cute for addressing this problem. So I don't know how many of you have seen the movie Saving Private Ryan, right? Popular a couple decades ago, about a family that sent 4 soldiers into World War II, and 3 of them were killed. And so they immediately organized a mission to rescue the last of the children, because it's considered it would be horrible if a family lost all of their children in the war. And there are still shades of this in the Army. Once, if a relative is lost, they try not to put the others, try not to put the siblings at risk. So how does this relate to Fibonacci heaps? Well, the thing is that it's not really the loss of that first node that creates a problem. The problem is when a tree starts losing nodes over and over again, so that there's a tremendous reduction in the size of that tree. And so the idea was, to fix this problem we have, is that if a node loses more than one child, then we actually want to take that node out of the line of fire. We don't want it to face any further risks. We will cut that node and move it to the roots of the heap ordered tree, of the collection of heap ordered trees. Okay. This is easy to implement because all we need to do is keep track of whether a node has lost a child. So we introduce a mark bit on each node, which is initially 0. We set it on the first cut, and we clear it when you cut yourself, when a node is moved to the collection of roots. Okay. And so the intuition about why this ought to be okay is that if we sort of ensure that a node only loses one child before we take it away, then all the nodes in the tree are going to have all but one of their children, and that ought to make the tree big. We're going to have to formalize that. But before we do, notice that our, our policy of removing the node when it gets cut, when it loses a child, may actually cascade, right? So if a node has lost a child, and so we cut another child and therefore cut that node. Well, its parent may have previously lost a different child, and so we'll have to cut the parent. And the grandparent may have previously lost a different child, and so we may have to cut the grandparent. And we're going to have to keep cutting all the way up the tree until we get to a node that has a clear mark bit. Right? And this is a bit worrisome because it means that our decreased key operation could have who knows what real runtime, right? We may be doing a tremendous amount of work as a result of applying these cascading cuts. So in order to analyze this, we actually have to do two things. First, we have to show that the cascading cuts are free, at least in an amortized sense. And once we have done so, we need to show that the tree size stays exponential in the degree. Of the root. So if we're able to prove these two things, then I claim we will have a working Fibonacci heap data structure with great runtimes for all of these operations. Does everybody see that? Are there any questions about why it's sufficient to demonstrate these two facts? No?
When you say exponential, when you say exponential and root degree, do you would 2 to the d over 2 count, or do we want to preserve?
Yeah, so that's the point. The base is unimportant in this exponent. How come? I mean, as long as it's bigger than 1. But why don't I care what the base is?
It'll still be O log of n either way.
Exactly. The base just goes into the constant in the runtime, right? If degree d implies size c to the n, right? Then the maximum size of a tree is going to be n, which implies that the degree is going to be order of log base c of n. Right? So as long as c is bigger than 1, and this is order log n divided by log c. So as long as c is bigger than 1, this is asymptotically order log n. Okay, good question. Any others?
By root degree, is this like, oh, it's, okay, yeah, it is root degree. For a moment, I thought it was any node in the tree degree. Okay.
No, it's specifically, right. So again, the rank of a tree is defined by the degree of the root of that tree. Okay. Other questions? All right. So let's look at step 1. I won't be able to fit it here, but I might as well start here. How do we show that the cascading cuts are free? Well, I'm going to define a potential function, right? And again, the idea of a potential function is that it sort of measures the amount of deferred work or the complexity of your data structure. It's something that increases when you acquire work to be done, and it decreases when you actually do work and simplify the data structure. So if what we're worried about is these cascading cuts, what might measure the amount of sort of pending work of pending cascading cut work that we might have to do in a particular tree?
the number of marked nodes.
Exactly. We're just going to define phi to be the number of marked bits. And remember, we have many trees. We just add up all the marked bits in all of the trees. Okay. So what, under this potential function, what is the cost of a cascading? Actually, let me change that. What is the cost of a decreased key? Well, what's the real cost?
The number of nodes you cut.
Right. Plus a little bit, right? So it's 1 for the initial work of, sorry, there's sort of a basic housekeeping work that needs to be done, right? I need to cut off the I need to cut off the nodes, but then I also need to well, no, I guess that's actually fair. Let's just say it's the number of cut nodes. Right? Oh, I guess plus the housekeeping, right? Where I have to change the value of the key. Sorry, let's just call that 1. Okay. What's the change in phi?
For each cascading cut, it would be -1, so around minus the number of cut nodes.
Exactly. Why am I cutting a node? Well, the first node is cut because of the decreased key. But every other node that I cut is cut because it has a mark bit set, right? So all except for the first node that I cut is being cut because it has a set mark bit, and I clear it when I cut that mark bit, when I cut that node. So I get a decrease in phi of the number of cut nodes. Sorry, let me tidy that up a little bit. I get a decrease in phi of minus the number of cut nodes minus 1. Okay, because I clear all of those mark bits. But that's not the only change in phi. What else changes the potential?
Like for the parent of the node that you cut. You
Exactly.
set that mark bit, right?
Exactly, right? I do this cascading cut, but eventually I stop. I stop when I hit a node that does not have a set mark bit, and I set that mark bit. So I add 1 to the potential by setting that last mark bit. So if I add these up, oh, look, I did put it on a slide. The total cost here is order 1. So indeed, my cascading cuts are free. Okay. Now, if you've been watching carefully, and we're here last time, you should have a complaint at this point.
You've created more root ordered trees that we have to deal with and delete min and stuff.
Good. So I created another heap ordered tree, right? So that sort of gets at the initial, that gets a part of the complaint. But what's wrong with creating another heap ordered tree? I mean, I already accounted for that with my previous analysis, right?
Well, we changed our potential function. And
exactly, right? In the middle of my analysis, I changed to a different potential function, right? And that's cheating, right? That's like saying, okay, I've got, I've run through my analysis and I've ended up with a really big number. So I'm just going to subtract a lot from it before I continue my analysis, right? I can't do that. I need to have sort of a consistent definition of the potential function that I'm using to define my amortized costs. Okay. So the problem was we had this old phi, which is equal to the number of heap ordered trees. And now I'm proposing a new phi, which is equal to the number of mark bits. And those are not consistent. I can't have it both ways. Okay. So what I need is a potential function that sort of attends to both of these issues. Right? So coming back to what you said, the problem with this cascading cut analysis is that at the end I create a new heap ordered tree. And so in a sense, if I don't do anything, I'm pulling free potential for the first potential function out of thin air by creating that new heap ordered tree and not accounting for it. So what I'm going to do is I'm going to double the second potential function. And this means that when I clear a mark bit, I don't get 1 unit of potential, I get 2 units of potential. And so I'm going to use one of those units of potential to pay for the real work. But I'm going to take the other unit of potential and use it to pay the first potential function for the new tree that I've created. Okay. So formally, what I can do is define my potential function to be equal to the number of heap ordered trees plus twice the number of mark bits. Okay. So now, I mean, the original analysis of insertion and delete min doesn't change the number of mark bits at all. Actually, it may remove one if the minimum key has a mark bit, but it doesn't increase the number of mark bits. So the original heap ordered tree analysis is just fine, right? But now if I consider the decreased key analysis, right, when I do a cascading cut, I do 1 unit of work, I increase the number of heap ordered trees by 1, but I decrease the number of mark bits. I decrease the mark bit part of the potential by 2. So the net change or the net work is 0 every time I do a cut, except for the last one where I set the mark bit. Is that clear? No questions about that? Okay, so now we have to do the second step, understanding tree size. Okay. So let's consider a node X, and let's consider its current children. Right? Some might be gone because of various deletions and cascading cuts that we did. Indexed from 1. So I'm going to call these y1 up to some yk. Right? My claim, so we're doing a lemma now, is that yi has degree at least I minus 2. Okay. So this is sort of, this is a lemma that's aiming to recover what we had from our tournaments, right? In our tournaments, we said that, well, if this node has degree d, then its children have degree d minus 1. And that lets us derive the exponential size bound because the degrees are not disappearing really quickly. Okay. So here we're saying, instead of having degree d minus 1, it still has sort of a large degree. And this is going to be enough to let us recover that exponential bound. So how do we prove this? Let's consider yi. What do we know? Oh, sorry, I didn't even specify the order in which I wanted to do this. Let's order these children by when they were added. So y1 is the first of the nodes, the oldest of the children, y2 is the second oldest, and so forth. And my claim is that the ith child, the one that was added in the ith place and still remains, has degree at least I minus 2. Okay. So let's prove this. Let's consider this ith child, this child that was added after the previous I minus 1. What do we know about this node? Why was it added?
It was added after the first I minus 1 children.
Exactly. It was added after y1 through yi minus 1. So what does that tell us?
At that moment, the node has a degree at least I minus 1. And so y also must have degree at least I minus 1 then.
Exactly. When it was added, x had degree at least I minus 1. Okay. It might have been larger, right? Why might it have been larger?
It may have a child that it hasn't lost yet.
Yeah, there may be some cuts in its future that remove nodes that have that were added before this one. But the degree was at least I minus 1. And what is our rule for adding, for consolidating nodes? Well, we only consolidate nodes of the same degree. So that means that yi minus 1 had degree at least I minus 1, right? Now, if degree, if y, sorry, yi, if yi had degree I minus 1 when it was added, what can we say about its degree now? Well, it's still in the tree, right? It's child of x. So what does that mean?
That at most one cut must have been performed.
Exactly. Only one child was cut from yi, and so that tells us that its degree is at least I minus 2. Clear? Any questions about that? So now we can forget how the lemma was proved and just remember that the ith node has degree at least I minus 2.
Oh, just to make sure, when you say degree, you mean like number of descendants, right? Not total.
I mean number of children.
Oh yeah, sorry, number of children, not including its ancestor, because it's also connected to that.
That's correct. I'm only looking downwards, right? So I'm not counting one for its parent. Okay, so now we have this bound on degrees. That's interesting. Okay, so now let's figure out how big trees are. Let's let SK be the minimum tree size of a degree K. Sorry, let me be more precise about that. Be the minimum number of descendants. So now we are talking about descendants, not children, and we're including ourselves of a degree K node in any tree constructed by our Fibonacci heap data structure. Okay. What can we say about these SKs? Well, what is the smallest possible value for S0, a tree with degree 0?
One.
Okay. What about S1, a tree that has one child? 2. Okay. Those are our bases. And now, if we look at SK, well, it's got a bunch of children, right? It's got k children. So I'm going to index from 0 up to k minus 2 of SI. Why am I going to do this? Actually, let me do it in 2 steps. So if I look at my children from the second child up to the kth child, right? The ith child is going to have degree at least I minus 2, right? So this is a, sorry, this would be a greater than or equal, right? And so now I can re-index this, go from 0 to k minus 2 of SI, right? So now to solve this, to get the upper bound, I'm going to solve an equality, right? I'm going to write SK equals the sum from I equals 0 to k minus 2 of SI. And now if I subtract SK from SK minus 1, right? This is going to give me a sum up to k minus 2 on the right, minus a sum up to k minus 3 on the right. So everything goes away except for the k minus 2 term, right? So why don't I just rearrange this? How do we solve this recurrence? And what a very important question are we answering with the solution of this recurrence?
The name of the heap.
Yes. Why is this called Fibonacci heap? Right, so these are the Fibonacci numbers. Right, and so we don't have to solve this recurrence because it was done for us. Right? And I'm going to assume that all of you have seen this. If not, you need to go off and find the derivation. S of k is phi to the k, where phi is, I am again redefining phi. This time it's the golden ratio, and it is approximately 1.5 something, right? Sorry, 1.6 something. Okay. And so we have proven what we needed, that the number of nodes in a Fibonacci heap is exponential in the degree of the tree. And we're done, right? This was the only thing that remember, our approach to decreased key was, well, we'll just cut the tree. We'll just cut the node, and everything about our previous analysis still works. The only thing that we got into trouble with in our previous analysis was worrying about the sizes of the tree that we ended up with. So as long as we follow the saving Private Ryan discipline, we will keep the tree size exponential in the degree, and therefore we will have all the bounds that we've already argued. So in summary, Fibonacci heaps give order 1 for insert and for decreased key, and order log n for delete min. Now this is optimal, unlike standard heaps, okay? Because you can't beat order 1 for operations. And the order log n for delete min is unavoidable. Why is that?
Because sorting is n log n.
Right. You can sort with n delete mins. So n delete mins have to take n log n time. Now, you get other operations for free with Fibonacci heaps. If you think about it, you can take 2 Fibonacci heaps and merge them into one very easily. How long does it take?
Oh, one.
Right. Good luck figuring out how to do that with a standard binary heap. Okay. And this is actually useful. I may come back to how it's used in a little while. All right. Now, you might ask, is this practical? All right. Should you be using Fibonacci heaps instead of binary heaps? The constants aren't bad, actually. Right? We haven't hidden any factors of a million here. Right? We have a small constant factor from the fact that we're using log base 1.6 instead of log base 2, but it's not terrible. Okay. And I actually, in a previous life, when I did experimental graph algorithms, have done experiments with using Fibonacci heaps as the minimum data structure for various graph algorithms, and sometimes they win. They can outperform, but there's a big difference. Why might Fibonacci heaps be a pretty bad idea for modern computer architectures?
Caches?
What was that?
The cache will be pretty bad.
Why will the cache be bad?
We're not using arrays or something.
Right. So Fibonacci heaps use pointers. Okay. Binary heaps are an instance of what are called an implicit heap. Which stores the keys in an array and just uses position in the array to tell you about the arrangement of the tree. Okay. And as was mentioned, modern architectures make really good use of caching, right? When you fetch a particular memory location, a whole bunch of the neighboring memory locations are pulled into your CPU at the same time. And that means that if you look at those other memory locations, it's free. Okay, in modern architectures, those memory accesses are generally the thing that determines the cost of a computation. And so, and this is at all different levels of the hierarchy. It's that accessing disk is incredibly slow compared to accessing main memory. Accessing main memory is incredibly slow compared to accessing your level 3 cache. Accessing your level 3 cache is incredibly slow compared to accessing your level 2 cache, and so forth. So you really want to have locality in access to memory. And the fact that Fibonacci heaps use pointers means that you lose that locality. And so that's quite likely to kill you if you try to use Fibonacci heaps as they are. Now, there has been a lot of research on implicit heaps to try and get better performance in implicit heaps, motivated by what you can do with Fibonacci heaps. All right. That is the story of Fibonacci heaps. But now I want to show you a little bit about how we can use them, right? So what was the original motivation for Fibonacci heaps? Right? It was Prim and Dijkstra's algorithm. So already Fibonacci heaps give us a significant improvement in the runtime for Prim or Dijkstra. So remember that if we use a regular heap, then the runtime for these algorithms was order m log n, right? Because we did an operation per edge, and each of those operations cost log n. What's the runtime if I use a Fibonacci heap?
M plus, again, n times log n. So
right.
we have m the decreased keys and n delete mins.
Exactly. So we have m decreased keys, but now they cost constant time. Whereas the expensive operations, delete min, we only do n of those. So the runtime improves to m plus n log n. And notice that this is linear, optimal, except when the graph is really sparse, when it has at most n log n edges. Okay. So that's quite a triumph, right? You just replace your data structure and suddenly you have an algorithm that is optimal for the vast majority of graphs that are out there. Okay. But theoreticians are never satisfied, right? We still have this n log n. And so, you know, somebody had to ask, can we do better, right? What about those sparse graphs? Can we achieve linear time for those as well? And so Fredman and Tarjan made some important progress towards resolving this question in the Fibonacci heaps paper. I mean, again, this really was the motivation for designing Fibonacci heaps. Right? So let's look at making MST and let's focus on MST. Let's look at making MST faster. Right? So let's reflect a little on why it is still slow with Fibonacci heaps. Well, it's because we're doing n delete mins. Right? But the fact that we're doing delete mins is not in itself a reason for slowness, right? The problem is that we're deleting from a size n heap, right? So each of those delete mins takes n log n time. Fredman and Tarjan had this idea. Can we keep the heap small? Because deleting from a small heap will be fast. So here's how you do this. We're going to choose some parameter k, our maximum heap size. Okay. And from a node, we're going to start running prim. Okay. Which means we're going to take that node into the minimum spanning tree. Now we're going to insert its neighbors. We're going to do a delete min to find the next node. That's going to cause us to insert its neighbors and do some decreased keys and so forth, right? And we're going to keep doing this until the heap size hits k. At that point, the heap is too big and doing delete mins from it is too slow. Okay. Now, heap size is kind of an internal thing to the data structure, but what does that heap size correspond to? Think about running Prim's algorithm and adding these neighbors. What nodes are in the heap?
How
All the
dense
neighbors?
the graph is or something?
Neighbors, right? So this heap is neighbors of the current tree. Right? So basically we run until we have k neighbors and then we stop.
So what do you mean by neighbors exactly?
Well, so when I'm running Prim's algorithm, I start at a node, and as I add nodes, right, I keep doing delete min to find the next node, and I add those nodes to the tree. But each time I add a node to the tree, I have some neighbors of that node which get inserted into the heap. Right?
So it stops when you reach k neighbors, essentially?
So I stop when the tree size reaches k, when the tree that I'm building has k neighbors that are not yet in the tree, but that are candidates for joining the tree. Make sense?
Yeah, thank you.
Sure. Yeah, keep those questions coming. So now I've decided, now I've reached a point where I can't keep running Prim's algorithm because the heap is too big. So what should I do?
Start at a new node.
Right. Start again at a new node that is not in a tree. Right? So basically I grow a first tree and I mark all of the nodes that get into that tree. And when that tree is too big or has too many neighbors, I start at a different node that's not in a tree yet, and I grow another tree. And eventually, I'm going to grow this new tree. Whoops. Until, now there's two things I have to worry about. One is that maybe I get k neighbors. The other possibility is that I join an existing tree. Okay.
Wait, I'm sorry. What was the first possibility?
Then I end up with k neighbors again, just like I did in the first.
Oh, okay,
group.
yeah, okay. Sounds good.
And eventually, all the nodes are in a tree. Okay. So now it appears that I've run out of work to do. I've grown lots of little trees, and each of them has a neighborhood that's too big for me to keep growing. So how can I make more progress? Well, what I'm going to do is I'm going to reset. I'm going to contract each tree to a node. So if you remember, when I was talking about minimum spanning trees, right? Once you've identified that an edge belongs in the minimum spanning tree, you can contract it and look for the rest of the minimum spanning tree in the graph that remains. So I'm going to contract each tree to a node. And now I'm going to restart the MST algorithm. Okay. Because notice that once I've contracted all of the trees, I've got sort of a new graph with a brand new minimum spanning tree problem. Okay. But I'm going to use a new K, a different boundary size parameter. And let's think about how I can play with those parameters. Okay, so what's the time for a phase when I'm using parameter K? Right. If I've limited the heap size to K, and I just run, from all these many different trees, run Prim's algorithm, but never let the heap size grow above K, what's the running time?
We have some number of delete mins, each of them take log k time, and the number of decreased keys, it's something less than m.
Exactly. We still have the same argument as we made before, that I'm going to have m decreased keys at most, because basically each edge is going to trigger at most one decreased key, right? And let me introduce a parameter t for the starting nodes and the number of nodes in this phase. Okay. So for each of those nodes, I'm only going to do one delete min operation, because then it's in a tree. Okay. Now the thing to notice is that I can make, I'm going to be spending m, I'm going to be spending linear time on the phase, just to look at the graph. But if I make t log k equal to m, that doesn't change the running time, right? My runtime overall is going to be linear if I have this relationship between t and k. Okay. So I can set k to be equal to 2 to the power of m over t, right? And still end up with a linear runtime. So this is how I'm going to choose my heap size parameter k. So now we know that it's going to be linear time per phase. The next question is, how many phases am I going to use? Okay. Well, notice that at the end of the phase, each node has k incident edges. Because it has k neighbors, and there's an edge to each neighbor. Okay. And that tells me that the number of vertices of the graph is at most m divided by k. So I have a recurrence now where I can say that the next t, right, t prime, is less than or equal to m over k. And that means that the k prime that I pick to go with t prime is going to be equal to 2 to the m over t prime. I now plug in t prime is equal to m over k, and I discover that the next k is going to be exponential in the previous k. Okay. So this is like a tremendous recurrence, right? We're used to recurrences where things divide by 2, where things subtract 1 or divide by 2. This is a recurrence where in each step, the degree exponentiates over the previous degree. Okay. Now, initially, the first t is equal to m, right? And so we're going to take k equal to m over n. Okay. Or let's say at least 2, just so that we don't start with a crazy tiny number. Okay. And now each time we run the algorithm, we're going to exponentiate each time. And so what that tells us is that the number of phases is equal to the number of times we have to exponentiate m over n to reach, when do we stop? What's the final phase?
When it's greater than n, then we
Exactly.
don't need to do it.
Right? If the degree, if our neighborhood size reaches n, we're done because we're attached to every single vertex. Okay. And this is represented as log star, as beta of m over n, which is just equal to the minimum value of I such that log iterated I times of m is less than or equal to m over n. And this in particular is less than or equal to log star of n, which is just, it just ignores the m over n part and says, how many times do you have to take the log repeatedly to get something below 2? Okay. And if you think about it, this is an incredibly slow growing function, right? Right? Its value is like, you know, 8 or something for the number of particles in the universe. Okay. And so for all intents and purposes, this is a linear time algorithm, right? So our runtime now, right? Each phase is linear, is just order m log star n. So we are insanely close to linear. Okay. And if the graph is a little bit denser, remember there's this m over n in here, so if m is somewhat larger, that just makes us even faster, even fewer phases. Okay. So that's great. But theoreticians are never satisfied, right? Log star n is not a constant, and so we have to keep going, right? So in some later work, a larger group of researchers improved this runtime to order of the log of beta of mn using a weird trick called edge bundles. So the idea of edge bundles was that when you're trying to be this fast, you can't actually afford to look at every edge every time. And so they actually found groups of edges that they could sort of order and say, I don't need to look at this edge until I've eliminated this other edge. So I put those edges in a bundle and I only look at the smallest edge in the bundle. Okay. And so, you know, now we've put another log factor in decreasing the function. In later work, a guy named Bernard Chazelle, who's a professor at Princeton, improved the running time to, oops, there's an M here, to m alpha of n log alpha of n, where this is the inverse Ackermann function. And the inverse Ackermann function is one of those crazy functions that only shows up in computability theory because it's so fast growing. Or sorry, the Ackermann function, it grows so fast that it only shows up in computability theory. This is so tiny that it's like 4 for the number of particles in the universe, right? So at this point, we're outrageously close to linear, but we're still not quite linear. And in fact, we're not sure if you can achieve linear unless you stretch the bounds of your algorithm a little bit. Turns out that if you add randomization, you can actually get a linear time minimum spanning tree algorithm if you flip coins to decide how the algorithm runs. But the weirdest thing of all about minimum spanning tree is that we actually have an optimal algorithm. An optimal deterministic MST algorithm, which was developed about 20 years ago. The problem is the runtime is not there. This is a very disturbing state of affairs, right? We know what the fastest algorithm is, but we don't know how fast it is, and we don't know if it's linear time. And for me, this is insanely frustrating because imagine if you work on this problem and you develop a linear time minimum spanning tree algorithm. So this is something that right now nobody knows exists. But Penny and Ramachandran can say, oh yeah, we had that algorithm already. So that's a little crazy. All right, so that's the end of Fibonacci heaps and minimum spanning trees. Are there any final questions about it?
How do we know an algorithm is optimal when we don't even know how fast it runs?
Yeah, isn't that interesting? I'm going to leave that for you to investigate. It's very tantalizing. Okay. Essentially, to be a little bit more formal, sorry, this is absolutely insane. It turns out that the the thing that keeps you from getting a linear time minimum spanning tree algorithm is handling the tiny, tiny trees that arise at the tail end of a recurrence of the style that I've already shown you. And so what Petty and Ramachandran proposed to do is, since they're only looking for an algorithm that needs to run for tiny, tiny trees, they actually propose to brute force enumerate all possible algorithms for minimum spanning tree for tiny, tiny trees. Run them all and see which one is the fastest. And once they've done that, they can use that as the base case for their minimum spanning tree algorithm. And since they're only doing it for incredibly tiny trees, that exhaustive search for the best possible algorithm takes linear time. So it's cheating. It's just horrible. It's an MIT worthy hack, is all I can say. Okay. All right. So that's the end of that story. Now let me switch to some logistical stuff. So first of all, I hope you all filled out the poll that was sent out regarding times for office hours. There will be office hours held immediately after class today on Commingle. And there's an entry in the course announcements page about how to join those office hours. Now, in general, when I create problem sets, I design them to cover the material through Wednesday with a little spillover into Friday of the week that I hand out the problem set. Because of the way we started on Wednesday, in this case, there's going to be a spillover to Monday. So there's one persistent data structure problem, which will be tackleable after you have seen Monday's lecture. And it's not that hard. So I wanted to flag that as an exception. Don't work on it now. But you don't have to worry about that going forward. Going forward, we'll have all of the material for the problem set done by Friday and most of it done by Wednesday. Okay. Also remember that we are forming collaborations, that we are sort of working on collaboration groups for the problem set. And as was announced on the course page, you should be signed up in PSET Partners. That's what we're trying this week. We'll probably try something else next week. But use PSET Partners, and anybody who is not matched by that PSET Partner system, we will take care of matching them by tomorrow. And we'll revisit that in office hours. So, any questions about the logistics before we move on to the next topic?
Is it Monday a holiday?
Sorry, Monday is a holiday. Oh, this is a problem. So we're teaching on Tuesday, which does not give you time to solve the problem for Wednesday. All right, I think what I'll do is just push that problem to next week. Okay, so that final problem in problem set 1, I'm going to defer that into problem set 2. Okay, and I'll put an announcement to that effect on the course page. So, topic 2, persistent data structures.
Sorry, but just before we move on, so for the PSET Partners thing, we have to sign up on the website, like even if we have a collaboration group, right?
That's correct. We want you using PSET Partners because there might be other people who are seeking who would benefit from being added to your collaboration groups.
Okay, sounds good.
Okay.
Thank you.
Sure. You may also find some collaborator who's so awesome that you want to abandon your current collaboration group. Who knows? All right. So persistent data structures. Nowadays, the motivation for this is pretty clear because we all use GitHub, right? And we all use Google Docs, and we frequently have to deal with versioning, right? So some data that we have evolves over time, and we want to go back to older versions of that data. And so Sarnak and Tarjan, this is the same Tarjan. Tarjan is basically the god of data structures. All the most awesome data structures were invented by Tarjan. This includes the union find data structure that you learned in undergraduate algorithms and many others. So Sarnak and Tarjan introduced this idea of persistence for data structures in general. And there was later work extending it by Sarnak and Slater and Tarjan. And you can find references in the notes if you want to read the original papers. And I encourage this because Tarjan is one of the best writers that I've ever seen of theory papers. And if you want a model for how to write good theory papers, Tarjan is a good one. So what Sarnak and Tarjan proposed to do was make data structures persistent. And what this means is you take a structure, any old data structure, and you augment it to support operations on past versions. So, for example, I might take a heap, and we already have operations on a heap, but what if I want to be able to ask, what was the min yesterday? Okay, that's not something you can do with a regular heap. But Sarnak and Tarjan showed how you can do a simple general purpose augmentation of a data structure to be able to answer that question. Now, this ability to query the past is what's known as partial persistence. But they introduced something even weirder. They also provide the ability to insert a new key in the heap yesterday. Okay. And then ask, what was the min 3 hours ago? And have it answered with the inclusion of the key that was inserted today. Right, so now we're doing time travel, and it's really hard to even explain, to even express what they're doing, right? But this is what they called full persistence, where you can query and modify the past. So, crazy idea that you would be able to do this. And even crazier, they came up with a way to do it that doesn't depend on what data structure you're using. They can do this for any, actually, let me stick with my board for a while. You can do this with any structure that is pointer based. So you have a collection of fixed size nodes whose fields hold values and pointers to other nodes. So all sorts of data structures meet this specification, right? The Fibonacci heap for sure, binary search trees, linked lists, right? These are all collections of fixed size nodes with pointers. There's one glaring omission, one sort of standard data structure that doesn't fit this model. What is it? It's actually so common that we don't even think of it as a data structure.
Arrays.
Arrays.
Right. No arrays. Right? You can't use the sort of indirect indexing that you use in an array, where you can look in the case place of the table as a function of k. All right. So what they're going to do is take any data structure, right? And what they are going to do is sort of wrap the data structure and the primitive operations on it. Right? So if the data structure is made up of these fixed size nodes, then the way that you modify the data structure is by changing a value or a pointer in a node. And any data structure operation is some collection of operations or also query a value or a pointer in a node, right? So when I do a search in a binary search tree, I am querying a bunch of fields of various nodes and using that to walk to other nodes and query their fields. When I do an insertion, I am modifying certain fields in certain nodes of that binary search tree. So if we can just find a general purpose way to modify fields in a persistent way that allows for versioning, then we can use that with any data structure. Make sense? So this is nice because we don't need to think about data structures at all. We just need to think about how to make a node persistent. So any thoughts on that? And let me emphasize here that you are not restricted to the pointer model that I just described. You can use, right, the data structure has to obey the pointer model, but we're going to use the full power of a computer, of a standard computer system to wrap the pointer operations. What's the most naive brute force way to version a piece of data?
Just remember everything in
Back up everything.
Yeah, just remember everything, right? So what I'm going to do is I'm going to change each field into an array of time value pairs. Okay. This is called the fat node method. Okay. So how can I? How do I do this? Right? I just maintain an array per field, and I add a value on each field modification. Right? That's pretty straightforward. And notice that this means that the runtime for a field modification is order 1, which is what it was anyway when we didn't have versioning. So this doesn't make things any slower asymptotically. But what does the cost? Where does the cost arise? How long does it take me to query a field of this data structure? And notice that I now have to specify a time as well as a field. So if I want to know what was the value of this field at this time, how long does it take me to answer that question?
Linear time?
So I can scan the array, right? And that will take order of the number of sorry, my pen is running out. So scan would be order t, order the number of time steps, number of modifications. Can I do better than that?
Binary search?
Yeah, I can just do binary search. Log t time, if there have been t modifications to the data structure. Okay. So not great, not terrible. Okay. now each query to a field, or each query to a field takes me log t time, where t is the number of changes. And so that is a multiplicative slowdown. That will hit every single operation in my data structure. So now a binary search tree will not take me log n time to find an item, it will take me log n times log t to find an item at a particular time, right? So that's unfortunate that we're paying this multiplicative log t cost. There's another cost that we do have to think about here. What else is not free? So we care about time for sure, but there's something else that we have to allocate for our data structure.
Memory.
Space.
Space, right? There's also a space cost. And so what is the space that we pay for each primitive update step?
Constant.
Right. So each time we make a change to a node, we have to grow an array by 1. Okay. Now I'm going to leave it to you to figure out, like, you don't actually, like, you can't just keep growing arrays. They'll run into other things. And so you have to think about, you know, allocating more space in powers of 2 and moving things around to keep it large. But that is a very simple analysis to show that in an amortized sense, you can keep the time, the time per modification and the space per modification constant, and pay this log t slowdown in the overall runtime. Okay, so this is sort of a straw man, right? It's kind of nice to realize that with only a log t slowdown, you can achieve full persistence in a data structure. But that's not good enough for theoreticians, right? In the data structures world, a logarithmic factor is a large factor because we're used to things running in log n time. And so if it's suddenly log squared n time, that's a lot worse. So what Sarnik and Tarjan figured out, and what we'll look at next time, is how to improve the running time of, improve the slowdown factor from a logarithmic factor to a constant factor, so that you can get persistence while only paying a constant factor in the running time of your data structures. That will be our topic for next time. And I will see you all on Tuesday. Don't sign in on Monday because I won't be here. Have a good weekend. Any questions before we all hang up?
The MIT calendar says that it's Tuesday classes on Tuesday.
Oh, really? We don't have a Tuesday? I thought we were getting Monday schedule on Tuesday, but maybe that's later in the semester.
Yeah, it's in October.
Okay, fine. Then I will see you on Wednesday. So it is certainly a good thing that I canceled that problem. All right. Enjoy your long weekend.
See you on Wednesday.
See you on Wednesday.
See you on Wednesday.
Thank you.
Is the pset available in the LaTeX version as well somewhere?
I can figure out how to do that. It'll take a little time, but we'll actually, that may be hard. That may not be possible given the way that we design our psets. I will look into it.
Okay, thanks.
Would there be a downloadable PDF available, or is that?
What, you mean you still use paper?
I mean, it's just nice to have a
that's so 90s.
Having NV.
No, we can definitely run up a PDF as well. I assumed most people would be working online and would prefer an HTML version of the notes. The pset itself, we can definitely enable PDF downloads for the psets.
Cool, thanks.
Sure thing. You'll be able to, if you go to NV, once I enable it, if you go to the NV dashboard, you'll be able to just click download on any one of the PDF documents. But remember, and let me say a little bit about NV, that people are asking questions there all the time and getting answers to them, so that the online document will have information that is extremely valuable for doing the psets or reading the notes. So even if you are working off of paper, I do recommend checking the online version frequently because it could save you a lot of work. Okay?
Are the groups for p-set problems like per problem or for the whole p-set? Like, can you work with different groups for different problems?
That's up to you. We are fine having you working with multiple groups, with different groups for different problems. P-set partners is of course going to assign you, is just going to do this one-off matching. As long as you are following the requirements for the class in terms of number of collaborators per problem, you can feel free to rearrange.
Okay, cool.
Okay. Any other questions?
Yeah, can collaborators be a directed edge?
No. Collaboration is bidirectional. Okay, and I will say more. A directed edge would just be would be a violation of our collaboration policy, because having one person tell somebody something else as opposed to working on it together is exactly the sort of thing that we don't want happening.
So what if like instead of telling them like the solution, they tell them what's wrong with like their existing solution or something?
So that is a form of collaboration, and it is still a binary form, a symmetric form of collaboration, and it's acceptable, but it counts towards your collaboration number.
Okay, I see.
Okay.